Welcome to the tutorial of this year's 30-day map challenge day number 7, where the topic is accessibility. To work out this map, I decided to work with public transport data, so you will see that we will collect publicly available GTFS data from New York City and then turn them into isochrones. For those of you who are new to isochrones simply mark those areas on a map which measure the same distance from a central point, usually measured in travel times. Let's see how we can build these isochrones about Manhattan, and then how we can turn it into a nice animation. In this tutorial, we are going to compute and visualize public transport data and isochrones around them. So first we will need to acquire public transport data. We will get that data from this website called Transitfeeds, which is a great repository for various public transport datasets all around the world. Here you can see all the feeds. Then within that you can pick your preferred geography, country, city. And then within cities you can also select different datasets and providers if they are available. For example, here I will focus on the MTA provider. That's one of the standard public transport operators in New York City, who are operating, for example, the famous or infamous New York City subway system. So from here, I downloaded the NYC subway GTFS dataset. Here you can pick any dump you prefer. I picked the latest one. I suppose that was the January dataset. Just click download and make sure that you store the dataset in the same folder where your Python notebook is running. Once you have the dataset downloaded, you can move on to the Python part and open your Jupyter notebook. Once we are in the notebook, as usual, I add the links here as well. So the full list of New York City data by the MTA provider and the subway dataset. And then we will do a few imports. First, the basic packages, GeoPandas, Matplotlib, and the rest. Then some geospatial and network analytics libraries, since for computing isochrones we will need to use NetworkX and OSM1X, which are able to collect network data from OpenStreetMap and also do various computations on that. And finally, a batch of visualization libraries, Contextali for base maps, ImageIO to export and create animated visuals, and IPython display to show them in the notebook. TQDM is to show the progress of any process, and for loop, so it probably belongs to the first group. So first we are going to prepare the GTFS dataset. Then we will develop a methodology to create isochrones around one randomly selected subway station. Then we will compute these isochrones for all the subway stations we have, and then we will learn how to create a nice visualization for every single isochrone, which is going to result in a series of images or frames, which at the end we will join into one single animation. First things first, let's prepare the GTFS data. Also, to make sure that we have the right framing, I will query the boundaries of Manhattan using OX. And then we will read in the stubs.txt from the GTFS folder, which is going to be a txt file, which, as you will see, contain basic information about all the public transport stops. Then we will have to turn this into a GeoPandas data frame. By packaging together the lat and long columns and turning them into the geometric column of the GeoPandas data frame. Here we can use this fancy function of GeoPandas, which is called points from x, y, which will simply package together these two columns and returns a list of shapely point geometries. And as you can see, after running this cell, we truly have a list of point geometries in the geometry column, and we have altogether 1,500 subway stations in New York. So, since we want to restrict our work to Manhattan so it remains a bit more manageable, we will have to overlay it with the admin polygon. But first, let's have a look and see what we have here. So, yeah, most of the subways are actually in Manhattan, and there are some here in Brooklyn, and I'm not sure, maybe this is Queens already. You can, and feel free to correct me in the comments, but we want to make sure that we are focusing on these parts of Manhattan only. So let's crop it by using the overlay function. We can also select the geometric column so we are not dragging along any additional info or field from the admin polygon. And this is how it looks like in Manhattan. Here we still have about 500 stations, which is still a lot. Then we can make this visualization nicer. For instance, we can define the canvas. This is still a bit too large for this screen. Yeah, still a bit too large. Yeah, this is it. And then we will use the built-in plot command, specify the axis. Let's just mark them by red for now and set a few more parameters, and also add a nice, smooth base map. And we can also give a title to the plot, switch off the axis, and show the visuals. And once it's rendered, it's a nice map of Manhattan with a base map underneath, showing all the locations of these subway stations. So now let's move on to the isochrone parts. So here what is going to happen is that first we select a random stop, so a random record from this data frame. There it is. Then we will create its center point as a tuple of coordinates, which is going to be the best and right input for the OX library, which is able to query a graph, a road network, for example, a walkable road network, if we prefer, and now we do, from a center point given as an input tuple and within a range of 1,000 meters. So if we do that, and you will see, we will get a decent road network. With about 2,000 nodes, and if we visualize it very quickly, then you will also see that this is actually a nice graph. So this is the area, and here you can see actually the central part. So this is the area within 1,000 meters from our target location. So yeah, actually I was expecting a circle, but I suppose it's a bounding box instead based on the 1,000 distance. Anyways, as a next step, we will compute the length of every single edge, which is every single road segment. And then for every single edge, we add a walk time attribute, which is simply computed based on the length of the road segment and an assumed typical walking speed. So now we will assign a minute value for every single edge line in this road network. Then we will move on to compute the isochrones. Remember, an isochrone is a boundary line which shows all the road intersections which are in the same distance from a center point. So, since we are talking about road segments and road intersections, we will need to get the center node, which is the closest point on the graph amongst these nodes, to our selected center point. Which is going to be a node ID. Then let's do a quick loop. So here we will compute isochrones for different time thresholds from 1 to 10 minutes, and for each of them we will store the results as polygons in the ISO polygons list. So first we will iterate over every single time threshold. And then we will use this very handy function of networkx, which will compute our subgraph, so all the nodes which are within a given radius, minutes, from the center node. And the reason we can give the radius in minutes is because we assigned an edge weight to every single graph, which is now measured in minutes. In case this part of the network calculations is a bit new to you or unusual, then I recommend you to check out my former tutorials on networks and graphs, and also my intro on networkx directly. Then once we have the subgraph, we will need to get the nodes and edges. And here now we are already working on our way towards creating the polygon. Then we will make sure that it's measured in meters using the Web Mercator projection. Buffer it, just so that we have a nicely looking polygon layer. And it's still in meters. And then we will just add it to the result list. Now let it run, and then we will visualize a few of these components. So for every element, we have a tuple containing the minute threshold and the polygon. So this is the first 1 minute isochrone, this is the 2 minute isochrone, this is the 3 minute isochrone, 4 minute, and as you can see, the polygon is growing, the shape is getting more and more complicated, and we are reaching more and more area from the same center point simply by walking around. And then the last one is this one. And here, as we are New York City, which has these very nice square grids, then actually we won't end up having a circle, but a nice square. And probably that's the reason we have a square here as well. So not because it's not circular, but because circular, using the Manhattan distance under the hood, results in a square. So now we have this list of polygons, which we can easily turn into one single geodata frame. And if we plot it with a certain transparency, then we will get this nice shaded thing. If we turn it to 0.1, then in theory the center should be, so isochrone minute 1 should be completely blue. The outermost should be at 10%. Now that we have it, let's create a nice visualization. This is too big again. Let's decrease the size. And now we will visualize the isochrones one by one. And based on their index, for every single one, we will get a unique color using, for example, the magma color palette, but you can use any other one if you wish. And then we will visualize the polygons. Since we are walking along road segments, the boundary lines we can reach are all streets and roads, and that's why we added the 25-meter buffer, so we don't have these strict lines, but we have these nicely shaped little buffered stripes. Let's also add the network edges with some faint gray color, and also plot the original stuff, so where we are starting from. Also, make sure we add our usual base map, and the final touch is title axis of tight layout. And this part might take a bit longer, but here we are. Yeah, there you go. There is the central part, there is our starting station, and there is this nice shaded and transient layer of reachability polygons or isochrones. So now we have the methodology to create one isochrone. And now I will do the same for a series of sample locations. From the previous pieces of code, there will be a number of functions I create and define. And again, these are functions which I simply asked ChatGPT to clean up my code and organize them in certain ways. So now I just copy and paste them, and you will find my code on Substack as usual. And also defining a few constants for the walking speed, the buffer range, and the two CRS views, and then all these functions here. Then, to make this notebook manageable and this tutorial not too long, I will take a sample of 10 randomly selected stubs. I will store their isochrones in this list. And I will iterate over all the randomly selected stubs to create the isochrones for each of them. Here we are doing the same thing. First picking the locations. Now we don't have a center, but we have multiple centers, so every stub will be the center of a set of isochrones. Then querying the graph, and then these graphs will essentially merge or come together if two isochrones will start to reach each other. Then compute the isochrones, create the final isochrone GeoDF, make sure that we have the stub name there as well, and then add it to the results. Now we can run this code. The TQDM, the one here, so it is showing us this nice progress bar. And even for 10 stops, it might take a few seconds, because if we take a closer look, you will see that now we are not moving in 1 second steps, but we are moving in 5 second steps from 0 minutes to 15 minutes. And the reason is that if we move from 1 to 10 minutes in 1 minute steps, then we will only have 10 different isochrones, which in an animation means 10 frames. However, if we have 15 minutes in 5 second steps, that means that we have, well, in 1 minute we have 12 frames. So we have 50 minutes times 12 frames. We have 180 frames, which at 24 FPS is about 7.5 seconds. So here you see that now we have 7 minutes left. So now I will stop the video and cut it, and I will be back once it's finished. So this computation has finished. So let's turn these isochrones, so this list of polygons, into one single data frame, and then start visualizing it. Here we will mostly use code from the previous rephrase. And first, just have a quick look on how this looks like. So now we should see about exactly 10 patches. As you can see, some of them started to reach each other, so that's how the random selection of 10 stations worked out. Later, I will show you what happens if we keep this script running for maybe 8 or even 10 hours. So that's how long it took for my computer to finish this on all the hundreds of stubs. But for now, let's work out a methodology on this smaller subsection. So first, we will need to dissolve the boundaries between polygons. So we will make sure that every polygon which belongs to the same time level as an isochrone is combined. So we are doing it here in a few steps. So first we will need to merge them and then dissolve the boundaries and then turn them into a final GeoPandas data frame. Here again, we are doing loads of relatively heavy geometric computations, so this code might run for a few seconds, but it shouldn't take that long as it took with the isochrone generation. In the isochrone generation, actually the tricky part or the long part is querying the graph and doing computations on the graph. So now it's still not that visible, but never mind. Now we will go for the final fine-tuned visualization. Change the size again. And the reason I'm changing the size again and again is that I have a prepared notebook on my primary screen and I am recording this on my secondary screen. So I'm copying codes line by line from my primary screen, and it's much bigger than the secondary screen, so that's why I always have to adjust the figure size. And then we will do the same thing again. We will iterate over the rows, over the tiers of different isochrones. And now it says minutes, but it's actually minutes and seconds, so, or not integer minutes, but minutes plus multipliers of 5 seconds. And here now you see that we have a much nicer coloring, much nicer gradient. And since the same time isochrones were merged and the boundary is dissolved, we see these patches. Maybe I zoom in after all. So these patches, when they start to touch, they will behave very nicely. Also, we can add the same thing, the base maps and titles and all those things. And see here, the boundaries are kind of getting washed away. So let's run it again with the base map, but then we are pretty much done with the static visualization. Yep. So this is how it looks like. Now we will do a few steps, some of them repeated steps, others are new, to make sure that we have a pipeline which is able to run through all the different minute values, so all the different isochrone layers one by one, and then we will run it through all the time or temporal snapshots we have, so that we will have a nice series of frames. And for each frame we will use the same visualization logic, and we will also export the result and save the file into this output directory. So once again, make sure that everything is combined. Now we will call them rings. We will do some simple coloring setup, so we have every single timestamp matched to a color. Then we will need to query the size of the final isochrone layer, so when everything is together. And this way we can make sure that every single snapshot, even the one where we just have 5 seconds isochrones, will have the same zoom and the same boundaries as the last one. So if we wouldn't add this part and wouldn't fix the image size, as you will see later on, for every image based on these values, based on these limits, then as we would keep adding isochrones, the total extent of the drone visuals would keep changing, just as we saw it here very early on. Yep, here. So as if we keep doing this, the total image would change and then we wouldn't be able to overlay them into animation. That's why we have to fix the boundaries and make sure that this fixed boundary aligns with the extent of the largest polygons. Then we will start to iterate over all the frames, again using our old friend TQDM. But before that, make sure this piece of code runs. It's long enough already. Yep. Let's just run it here and then iterate over all the temporal snapshots. We can also add some descriptions so the TQDM function also says what it's doing. Then we will create an image. Then we will iterate through all the rings, all the isochrones, up until the temporal threshold of that certain frame. Then we will set the limits. We will add the base map, and here you can probably see that this code was reformatted with ChatGPT, so that's usually very helpful when I have a longer piece of code. We just have to make sure that it doesn't make anything up. Then make sure it's base map here. Plot limits are set. Then we will add a little counter in the top left of the image, which we will show the minutes and seconds as well. And we will use the regular text box, which you have probably seen in a couple of my tutorials before. We have to specify the X and Y position in terms of proportions to the whole image. The label, the text we want to show, which we created here, so it shows the minutes and the seconds. And then how it should be formatted, font size, whether it should be bold, color, and then the bounding box behind it. So if it should be present at all, what color should it have, and stuff like that. And then we will do further styling to make sure that the image has the right size and the right aspect ratios. And then we are nearly there. We just have to save the image. So now I just run this code for a few minutes, but now let's stop it and I will go for another directory where I have already prepared all the frames. Here you can see that for now we have prepared about 50 frames, but originally we should have more than 150. So first we will need to define the output file, which is going to be a video in an MP4. Then we will need to query and organize all the frames into one single list. Then we can use the image.io library very quickly to turn these images into a list of image objects. And then we can simply use the image.io library to save this series of images at a certain frame per second rate into a video file. Once the video is exported, we should be able to load and view it right here in the Jupyter notebook. Just like that. And as you can see here, my estimation that we will have about 5.5 seconds of footage if we go for a 24 FPS frame rate and 5-second isochrones. And then we actually have it here. We can also zoom in. Its resolution is pretty good. And we can keep running it. We can increase the width here as well. So yeah, briefly, or maybe not that briefly, because this was quite a long tutorial and quite technical with loads of codes and loads of heavy functions. But we have arrived at the end. I hope that you also have a nice Manhattan isochrone map like the one here. You can experiment with other cities, other color maps, and other time ranges as well. I'm sure this would look nice on a country level scale in an hourly resolution, for example. And if you use that and create those, make sure to let me know and I can feature them as well. And for the code, as usual, go for Substack. Thank you for watching and see you next time.